Hello everyone, my name is Peter Reithofer. Today I will talk about handling material scatter. I'd like to give you some case studies. Normally I like this event. We have good face-to-face meetings, but as you know, due to COVID situation, we have to do this over web meeting or video conference, and I hope you can enjoy this event too. Yeah, I will start with the presentation now. So, as you know from the CAE Grand challenge, we always get a challenge, a software vendor to answer on the challenges from the industry. And as you see, I figured out what answers I would like to give on these questions. Mainly I want to talk about material scatter, the influence of physical testing, and how we could handle data in an efficient way to look on scatter and reliability and so on. Therefore, I have some examples for you on foamed plastics and short and long fiber reinforced plastics, and hope that this is interesting for you. First of all, I would like to give you a rough overview about our products. As you may know, we have some software products, especially Valimat, where we can make material cards from test data to a validated material card. And from the testing side, we are offering a testing device, a desktop device, where you can do efficient dynamic testing. More on this later on. These products, what we are offering, are intended for different materials. Here you can see what are the main regions where we can use these products. Now I just want to talk a little bit about scatter. Is it just a lack of information? Because we don't understand the physics behind? We have too less knowledge on it? Or is it just because we have too less specimen available to make research, or too less money or time to look on it? In the simulation, we have always the situation that we have the reality, which is quite complex, and in the simulation we have the ideal world. And often we don't know about the process, about the real geometry and the real material behavior, because we can't consider that. And that can be perhaps a matter of scatter. What can we offer here? So I mentioned already Valimat. In Valimat, we can store all this test data coming from static and dynamic tests, even not only force displacement or other values, even pictures and DLC evaluations and so on. And all with this information on the test, we can automatically generate a simulation model for a certain kind of solver. And based on this simulation model, we can set up an optimization procedure to get a material card out of this workflow. And as we have built up automatically a LS-op job with all this information in the background, it's also just a click to switch to a design of experiments or to switch to Monte Carlo simulation to look on what is happening if we have some probability, some distribution in the input, how is this affected on the output. We have our products on the one side, on the other side we are offering service. So you can also come to us for making services. So if you deliver us granular, we automatically generate samples, do the testing, and finally deliver material cards. Out of this procedure, I have two examples for you. One is coming up from the side of pedestrian safety. You can see a head impact on a grill. And over the last 15 years, in the beginning, there was the focus on the deformation behavior. As you can see, the simulation without failure and the test curve, we have a quite good correlation in the beginning. Nowadays, customers expecting to predict also failure, but it's always a deterministic failure what we consider here. So often it is a good example, as you can see here, but sometimes it doesn't suit together. And what is the reason for it? Second example what I have here is coming from the electronic industry. Here we considered the process by taking the process simulation into account in the structural simulation with a drop test of this electronic control unit, and we wanted to predict the failure. And here you see we are looking on probability, and already we can see, if we consider that we can get quite close from the simulation side for a pass or fail in the behavior. So depending on the possibilities, it's mainly meaning how big is the simulation model, and if you focus only on this part, on a big, it's possible to already consider these effects. So now I would like to give you some examples to have a closer look on the material behavior, to see what is happening and to understand what are effects coming from material. So here we have a physically formed plastic part, and as you can see through this process we get the distribution of bubbles in the location, over the thickness, in the volume, in the size, which affects that we can have a mass reduction, what we want to have for a lightweight product. But this mass reduction is a local situation what we have coming from the process, and this will also mean that this will affect our mechanical behavior. So for this example we did some bending tests. We cut it out some samples from plugs in a small size, without foaming, in compact format. That's the green curves. As you can see, no deviation in the measurement of this deformation behavior. The red curves, the samples are cut out from a real part, and blue, that's the foamed part. And as you can see, through this process we get a big deviation, a big scatter. And now how we can consider this? So our software solution offers you the possibility to make statistical evaluation. You can easily plot the confidential interval of the test curves. That's the upper right chart. In the lower right chart you see the evaluation of the extreme values, and this can then be used to find out if my material cut I generated is in this bounds or not, something what you can easily use. What we can also do is, with our software solution, we can set up quite easily a part composite material with skin and core material properties, and that could be easily a starting point for stochastic analysis. Here exemplary you can see the compact behavior and how it will change if you vary the thickness of the skin and the core and the percentage of gas in the core. And if you consider all this together in a material card, you can see you can quite good predict this behavior by considering everything of this. But it's your choice to go this in more detail with considering the process. The other opportunity would be to make it more on a stochastic approach. Now I want to go to the next material, to the domain of the short and long fiber reinforced materials. As you know, we have anisotropic material behavior, and in this example we have injection molded samples, so highly orientated. Without cutting it out, it's injection molded one, and we have roughly 20 tests, all tested on the same condition at 2.5 meters per second. And as you see, quite good overlay in this stress strain curve. The deviation is in the failure, what is typical and where we want to make more research on it. So what opportunities, capabilities we have now here? So one of them is that we can easily evaluate a certain failure probability with Valimat. As you can see, we can easily plot 20, 50 and 80% failure probability, and we can use this to make a material card a failure criteria for 20% failure probability, 50 or 80%. That's straightforward. That's a deterministic approach. What we can furthermore do is, if we simulate it, as you can see in the left chart, you can see the simulation curve without failure criteria, and we can plot on the simulation curve the failure points, what we have measured in the test region, and visualize it easily in our software. And we can copy these values for further evaluations just to Excel or to R, as you can see in the right chart, where we have a Y-bull diagram for the failure probability over the failure strain. Now I would like to go to more sophisticated work. This was done by Nicolas Sügursch. He was focusing on short fiber reinforced plastics, and he used a consultative approach for simulating it. So mainly he did lots of tests on a polypropylene 30% glass fiber field. He did lots of 3-point bending tests for different orientation, at least 30 tests for each orientation and speed. And he could use these tests to make research on a stochastic rupture probability. And he compared this deterministic to probability approach, and he did some research on the influence on the Monte Carlo simulation. As he is using a constitutive flow, he could only look on the principal strain as a failure criteria. So, and therefore you see here in the Monte Carlo simulation, the rupture strain is the main influence on how much deflection you can achieve in the 3-point bending test. And you can see also in the distribution what he measured for the deflection, it's in the same region as he has used this distribution for the rupture strain. So the input leads you to the same distribution in the output, because the scatter in the input that defines mainly the output scalar. So the main effects were considered in this approach. We did some further investigations, not only to look on the deflection and the global research. Currently we have done some 3D digital image correlation. Therefore we're using 2 high-speed cameras to measure the deformation. And here you can see 2 pictures of the cameras, and out of this we can measure the strain field 3-dimensional. And here you see some hard facts what we are using. And here you can see first results, quite interesting, for 2 different types of fiber reinforced materials. One long glass fiber polypropylene and one short glass fiber for polybutylene terephthalate. We variate the orientation of the cutted out sample all in the same position, and you can see over the orientation of the sample for the same loading conditions, we get a difference in the maximum strain measured, mainly quite constant over the region from 0 to 50 degree. At 90 degree, especially for a long glass fiber reinforced, we get higher strain values. What is currently in further research, as we don't know if this is influenced of this fracture behavior and the measurement. If you want to go more close and deeper, we could also use a microscale approach, which is provided by MAT 215 in LS-DYNA. This material model is based on a homogenization and a Mori-Tanaka mean field theory. So we take the fiber and the matrix material itself into account. So if you're using such a material model, as you see, you can quite good describe the material behavior, what you measure for 3-point bending for different directions and for the puncture test. So quite close agreement between the simulation and the averaged test curves. But what is the advantage here? So as we know for this material class, the process induces the different fiber orientation based on the shear and the locational flow. And also this can be considered, as you can see in this diagram on the right lower area. Furthermore, we know from the manufacturing that we have a fiber breakage, so we have a fiber distribution in it. And also we have a distribution, the fiber content, based on the delivery, based on the molding itself. We have different content on each area in a part. And if you take this into account, we can look at the material itself and the keyword. We see the composite build-up, and the composite build-up shows us the opportunities that we can define the fiber volume fraction, we can define the fiber length, the fiber diameter, and the fiber orientation itself. We could use these values for a Monte Carlo simulation to make deeper research, to get a deeper understanding how this parameter affects our material behavior, our part performance, and so on. That's just the idea and outlook. So if you're interested more in this material model, I have given you a link to our summer school where we are talking in more detail on it. Here you see then the automatically generated LS-Object out of Valimat, where we then can define this distribution for these fiber values in it. I'm coming to the summary. Exemplary, I showed you some main influences coming from the material, from foam plastics and fiber reinforced plastics. I could introduce shortly you some features of Valimat, how it's possible to make statistics, average curves, evaluate extreme values and show the confidence interval. We can easily set up automatically a Monte Carlo simulation with LS-Opt. And Impetus itself, the testing, offers you also an efficient way to measure 3D strain measurement, because we need this all together. If we want to make deeper research, we need more data. And finally, I showed you a micromechanical approach, which offers you the opportunities also to make a Monte Carlo simulation on this kind of materials. I hope this roughly 20 minutes were interesting for you, and thank you for your attention, and I would be free for any questions now. So thank you very much.